Why do SpaceX's rocket engines look so different from NASA's? I mean, just look at them. NASA's rocket engines are usually huge, incredibly complex, and covered in pipes, valves, and hardware. Then you look at SpaceX's Raptor, and it almost looks unfinished. The surprising part is that both engines power some of the biggest and most powerful rockets ever built. So why do they look so different? Is one actually better than the other? Or were they simply designed for completely different missions? Honestly, there is no better way to find out than just putting NASA's and SpaceX rocket engines head to head, comparing everything from their design and power to their efficiency, cost, and reusability to find out exactly why they were built so differently, and which engine truly comes out on top. So first, let's talk about the NASA engine that's basically a celebrity in the space world. It powered the Space Shuttle for decades, and now it's back as the muscle behind NASA's giant moon rocket. I'm talking about the RS-25. From the moment it first roared to life, this hydrogen-fueled engine was pretty much destined to become America's workhorse for human spaceflight. And honestly, it's one of my favorite rocket engines ever built. It just has that, they actually pulled this off, kind of engineering that makes it ridiculously cool. The job NASA gave it wasn't exactly easy. For starters, it had to work both at sea level on Earth and later in the vacuum of space. Then there's the throttle. Most rockets just light the engines and go full send. The Space Shuttle couldn't do that because it wasn't just launching a pointy tube, it was launching a giant space plane with wings. As it climbed higher, the engines constantly adjusted their power to keep everything under control instead of treating the atmosphere like it owed them money. But the biggest challenge was reusability. Back then, rockets were basically the paper plates of the space industry. You use them once, toss them away, and hope they landed somewhere unimportant. The shuttle, on the other hand, was supposed to come home, land on a runway, and fly again. That meant the engines had to survive launch after launch without mechanics needing to rebuild them from scratch every single time. So, how on earth did engineers manage to build something that could do all of that? Well, they built one of the most complicated rocket engines ever made. The RS-25 utilized a highly complex, fuel-rich, staged combustion cycle, which means it takes both liquid hydrogen fuel and liquid oxygen and sends them on what feels like a giant road trip through the engine. It takes detours, loops around, cools parts of the engine, spins turbines, and only then ends up where it's actually burned. First, the liquid hydrogen and liquid oxygen flow from the rocket's main tank into the engine. Before they can burn, both liquids have to be squeezed to an incredibly high pressure by powerful pumps. These aren't ordinary pumps either. They're powered by tiny turbines spinning at tens of thousands of revolutions per minute, faster than the engine in almost any race car. Once the fuel and oxygen are under pressure, they each take different paths. The liquid oxygen heads towards small chambers called pre-burners. There, only a tiny amount is burned to create extremely hot gas. That hot gas doesn't make thrust yet. Instead, it's used to spin the giant turbines that drive the fuel pumps. Think of it like using a small engine just to power an even bigger engine. The liquid hydrogen has another important job before it burns. It first flows through tiny tubes wrapped around the engine's combustion chamber and nozzle. This cools the metal because without it, the engine would literally melt itself in seconds. At the same time, the hydrogen heats up, so when it finally reaches the combustion chamber, it's actually more efficient. After all those detours, the hydrogen and oxygen finally meet inside the main combustion chamber. They mix together, ignite, and create super hot gas that shoots out of the nozzle at incredible speed, producing the thrust that launches the rocket into space. It's an unbelievably complicated process, but thanks to all those extra steps, the RS-25 squeezes almost every bit of energy out of its fuel, making it one of the most efficient rocket engines at the time. To put that into perspective, it has a specific impulse of 452 seconds in the vacuum of space, meaning it gets more thrust from every kilogram of propellant than almost any other chemical rocket engine. It can also throttle anywhere from 67% to 109% of its rated power in precise 1% increments, giving engineers incredible control during flight. Even more impressively, different parts of the engine operate in temperatures ranging from a freezing -253 degrees Celsius, where liquid hydrogen is stored, to over 3,300 degrees Celsius inside the combustion chamber. Those are remarkable numbers, not just for its time, but even by today's standards. Now, what about reusability? This is where hydrogen fuel really starts showing off. If you burn kerosene, as many older rocket engines did, you end up with a lot of soot. That's not a huge problem if you're throwing the engine into the ocean after one flight. But if you want to use the same engine again, nobody wants to spend days cleaning out what is basically rocket chimney dust. Hydrogen is different. When liquid hydrogen burns with liquid oxygen, the main byproduct is just water vapor. That's about as clean as rocket engines get. It is also one of the huge reasons it can use the closed-cycle design. Since hot gas is sent back into the main combustion chamber to make even more thrust, a clean burn makes sure there's no soot clogging up the engine. Less fuel is wasted, more energy is turned into thrust, and the engine can produce incredible performance without becoming huge. In fact, the RS-25 was compact enough that NASA could fit 3 of them onto the back of the Space Shuttle. Sadly, when the RS-25 flew on the Space Shuttle, it was designed to be reused again and again. But today, on NASA's Space Launch System, those exact same engines are only used once. After each launch, they fall into the ocean along with the rocket's core stage, just like traditional rockets. So, after spending decades building one of the world's most advanced reusable rocket engines, NASA now throws it away after a single flight. Space can be weird sometimes. Of course, the RS-25 didn't stay the same forever. Over the years, NASA kept upgrading it to make it more powerful, more reliable, and easier to maintain. Engineers improved the combustion chamber, strengthened the welds, redesigned the turbopumps, and made dozens of smaller changes behind the scenes. One of the biggest improvements was its throttle range. The earliest versions could produce what NASA called 100% power. Later versions pushed that to 104.5% during normal shuttle missions, and if there was an emergency, they could briefly reach 109% or even 111%. Today, the RS-25 engines flying on NASA's Space Launch System normally run at 109% power to give the massive moon rocket the extra thrust it needs. Now, I know what you're thinking. How can something go above 100%? Did NASA accidentally invent 109% of 100%? But there's actually a perfectly reasonable explanation. The original 100% wasn't the engine's absolute limit. It was simply the performance target engineers set when they first designed the engine. Later on, after years of testing, they discovered the RS-25 could safely produce even more thrust than they originally expected. Instead of renaming everything and confusing decades of reports, NASA kept the original definition. So the engine became capable of running at 104.5%, 109%, and even 111% of that original rating. Keeping the old scale also made it much easier to compare data from different tests and shuttle missions. Otherwise, every old document would need an asterisk saying, well, this used to be 100%, but now 100% means something else. Engineers hate that kind of paperwork almost as much as they hate exploding rocket engines. There was one catch, though. The harder you push any engine, the more likely something goes wrong. Tests showed that once the RS-25 went much above 104.5%, the chances of a failure started rising much faster. That's why the Space Shuttle usually stayed at 104.5%, only using the higher settings if the mission absolutely needed the extra performance. The SLS is a different story. Since its engines are only expected to survive one flight, NASA is comfortable running them at 109% for the entire launch. Overall, the RS-25 is a fairly reliable and impressive engine. It has been used for more than 3 decades, helping complete 135 shuttle missions and 2 Artemis missions. Over its lifetime, the engine accumulated more than 3,000 starts and over 1 million seconds of combined ground testing and flight time, making it one of the most thoroughly tested large rocket engines ever built. So, with all of that in mind, how did SpaceX manage to build an engine that's even better? Well, they clicked the subscribe button. Just kidding. But seriously, if you're enjoying the video, consider subscribing. It's a lot easier than building a rocket engine. Anyway, SpaceX looked at almost everything that made the RS-25 special and asked, what if we took it one step further? The RS-25 is famous for 4 things. It's reusable, it's incredibly efficient from liftoff all the way to space, it uses a staged combustion cycle, and it operates at extremely high chamber pressure. Those are already some of the hardest engineering challenges in rocketry. SpaceX didn't ignore any of them. They tried to improve all 4. The biggest leap came with the engine cycle itself. Like the RS-25, the Raptor uses a closed-cycle design, meaning it doesn't waste the hot gases that power its pumps. But instead of having one gas generator, Raptor has two. One powers the fuel pump, while the other powers the oxygen pump. This is called a full-flow staged combustion cycle, and no rocket engine had ever successfully used it in flight before Raptor. It's like replacing a car with one engine driving everything with a car that has two perfectly synchronized engines, each doing half the work. It's much more complicated to build, but if you can pull it off, you get far more performance. And the numbers are pretty incredible. The legendary F-1 engine that sent astronauts to the moon reached about 100 bar of pressure inside its combustion chamber. The RS-25 doubled that to just over 200 bar. Then SpaceX came along and pushed the Raptor to around 330 bar. That's more than 300 times the air pressure you're feeling right now, just sitting on Earth. All that pressure translates into more thrust without making the engine dramatically bigger. A single Raptor 3 can produce around 250 tons of thrust at liftoff, and even more in vacuum, while also achieving one of the highest thrust-to-weight ratios of any large rocket engine ever built. In other words, it's ridiculously powerful for its size. But SpaceX didn't stop there. Instead of using hydrogen like the RS-25, Raptor runs on liquid methane. Now, hydrogen is still slightly more efficient, but it comes with some pretty annoying downsides. It's extremely difficult to store, it leaks through the tiniest gaps, and it requires enormous fuel tanks. It's a bit like trying to transport a cloud inside a shopping bag. Methane is much denser, much easier to handle, and it still delivers excellent performance. It also burns much cleaner than kerosene, making it a great choice for engines that are meant to fly over and over again with very little maintenance. Another impressive thing about the Raptor engine is just how much it can move. The RS-25 used a giant ball and socket joint called a gimbal bearing that allowed each engine to swivel and steer the Space Shuttle. It could pivot by about 10.5 degrees, which was already considered an impressive range. So when you first look at Super Heavy with 33 Raptor engines packed so closely together, you'd probably assume there's barely any room for them to move. I mean, they're practically shoulder to shoulder, but that's not the case. The engines in the center of Starship and Super Heavy can swivel by up to 15 degrees, giving them even more control authority than the RS-25. That's a surprisingly large amount of movement for engines packed so closely together. And because those engines are moved by fast electric actuators, they can react almost instantly to keep the vehicle balanced. Even if the rocket starts to drift or tip slightly, the engines quickly swivel to push it back on course. That makes Starship not only enormous, but surprisingly agile. Then there is also an advantage that is something you don't really think about until you're already in space. Raptor can restart in space. Raptor uses a modern ignition system that allows it to restart multiple times in the vacuum of space. In fact, SpaceX has already demonstrated this on Starship test flights, successfully relighting Raptors after long coast phases to perform additional burns. Multiple in-space restarts give Starship the flexibility to perform complex missions instead of just one giant burn. The RS-25, however, was never built for that job. It uses pyrotechnic igniters to start the engine. Think of them as extremely powerful one-time matches. Once they're used during launch, they're gone. There's no button you can press later to light the engine again. If the astronauts needed to change their orbit or come home, they didn't use the RS-25 at all. Instead, the shuttle relied on a completely separate set of orbital maneuvering system, or OMS, engines mounted at the back of the spacecraft. And finally, we get to what might be Raptor's biggest advantage of all. Not performance, not thrust, not even reusability. It's how easy it is to build a lot of. The RS-25 is an engineering masterpiece, but it's also incredibly expensive. In more than 40 years, fewer than 50 of them have ever been built. Even today, each new engine costs NASA somewhere around $150 million. That's enough money to buy a fleet of private jets. Or one very, very fancy rocket engine. Part of the problem is that the RS-25 was never designed for mass production. It's an incredibly complex hydrogen engine with thousands of precision parts, and for most of its life, only a handful were built each year. NASA has found ways to reduce the cost using modern manufacturing techniques like 3D printing, but when you're building so few engines, there's only so much money you can save. SpaceX took the opposite approach. From day one, the Raptor was designed to be built by the hundreds, not by the dozens. Instead of treating every engine like a priceless museum piece, SpaceX designed it so it could roll off the production line quickly, cheaply, and over again. Today, the company has already built hundreds of Raptors, with production rates reaching more than one engine per day. And the cost difference is almost hard to believe. A single Raptor is estimated to cost somewhere between $250,000 and just over $1 million, depending on the version and production stage. That's still a lot of money, but compared to an RS-25, it's almost bargain bin pricing. Now, to be fair, this isn't a perfect apples-to-apples comparison. The two engines were built for different vehicles, different missions, and under completely different government and commercial programs. But no matter how you compare them, the gap is enormous. So now that we've gone through all the differences between these two iconic engines, we're finally ready to answer the big question. Why are they so different? The answer is actually pretty simple. Because each engine was built to match the dream of the rocket it powers. The RS-25 was designed during the 1970s, when NASA wanted to build the world's most capable reusable space vehicle. Its mission was to launch astronauts safely, deliver massive payloads to orbit, and do it with incredible reliability. Performance came first, cost came second. And for that mission, the RS-25 was almost perfect. It became one of the most efficient rocket engines ever built, survived dozens of flights, and set a standard for reliability that few engines have ever matched. Even today, after decades of upgrades, it's still powerful enough to send astronauts back to the moon aboard the Space Launch System. But Starship is trying to solve a completely different problem. Elon Musk's vision isn't just to visit Mars once every few years, it's to make spaceflight as routine as flying across the Atlantic. That means carrying huge amounts of cargo and people into orbit, flying to Mars, landing, making new fuel on the planet, flying back to Earth, and then doing it all over again. That's an almost impossible list of requirements. To pull it off, the Raptor had to combine the raw power of the Saturn V's F1 engine, the efficiency of the RS-25, the reliability expected from modern rockets, and package all of that into an engine that could also be built quickly and cheaply. NASA built 5 operational space shuttles, each powered by 3 RS-25 engines. SpaceX wants to build around 1,000 Starships, each with up to 6 Raptors, plus hundreds of Super Heavy boosters carrying 33 engines each. We're talking about thousands upon thousands of engines, not dozens. That's why Raptor was designed with modern manufacturing in mind. It takes advantage of technologies that simply didn't exist when the RS-25 was created, like advanced 3D printing, newer metal alloys, and decades of improvements in computer simulations and testing. Its methane fuel is also much easier to store and load than liquid hydrogen, making launch operations faster and less complicated. And then there's the reason SpaceX chose methane in the first place: Mars. Natural gas on Earth is mostly methane, and Mars has everything needed to make it too. Its atmosphere is rich in carbon dioxide, and beneath the surface is plenty of frozen water. Combine carbon dioxide with water using electricity, and you can produce both methane fuel and liquid oxygen. That means a future Starship could land on Mars, manufacture its own fuel using local resources, and fly all the way back to Earth. So, Raptor or RS-25? Which one is the better engine? Well, this time I will let you decide in the comments below.